Hello, my name is Owen Zonneveld, and this is my paper for computer networks, and it is about distributed road networking. So this algorithm relies only on vehicle-to-vehicle communication. So cars propagate road network knowledge directly to one another. This avoids the need of a centralized server, so there's no need to be connected to the internet. Cars can communicate so long as they are within range of one another in this system. So as you can see, these two roads have these little circles around them representing their communication range. And since they're both within each other's respective circles, they can communicate. An interesting property of this is that once a car has traveled along a road, it has a ground truth it can use to validate the information provided by other peers in the network. So it could catch people lying to it essentially. Another interesting property is that cars might not be close in the network space, but they might be close in physical space, so they can still communicate. And in this example, you can see the two cars, there's no roads that directly connect them, but they can still talk to one another, which has a couple interesting properties. But first, we'll be using a simulator to test this. So this simulator generates a new road for each run. And there are a couple key assumptions this simulator makes. So firstly, cars can uniquely identify all roads in the network. They just have a common way of referring to each road. Secondly, the road network does not change, so roads are neither created nor destroyed. Another property or assumption is that all cars follow the laws perfectly. They do not speed, they do not run red lights, they do not cut people off. It's just assumed everyone is perfect, and that kind of extends to there being no maldoers in this simulation, which isn't perfectly accurate, but I'll get to that later about how we could possibly deal with that. And the last assumption is that cars travel randomly. In the real world, people are in cars to drive places, whether they're going to work, school, or some other place. But they're in their car to go somewhere. In this, they just reach a junction and they just decide to go in a random direction. But so this could be a source of inaccuracy, but there can be extensions to this paper to see if that uh, to see what changes when you actually implement kind of more of a system like that that represents humanity better. So about these maldoers, so this is a theoretical communication protocol to kind of deal with them, so we don't have to worry about them so much. The way this works is by there's two steps. So first, both vehicles encrypt the data they're going to send to the other one, and then send that encrypted data over. Once both vehicles have received the full encrypted packets, the vehicles send each other the decryption keys. So this essentially allows both vehicles to learn about what the other vehicle knows about at the same time. And what this avoids is that if one vehicle, like a maldoer, knew what the other vehicle had already traveled on, it could know what to lie about, like what it can lie about without being caught, essentially. And we do not want that. We want to avoid that. So in this system, the maldoer just has no idea what road they've been on. So trying to lie about it is a lot riskier. Because if it lies about something the other car knows about, then the other car will immediately just reject whatever it sent. And the maldoer won't have the effect it would want it to. So to measure the performance of the algorithm, we're going to be measuring the average road network knowledge of all cars in the network every tick of the simulation. So the road network knowledge is pretty much just the amount of roads the car knows about over the total amount of roads in the network. So if it knows about 10 of 20 roads, that would be 0.5. And there's going to be a couple tunable variables we're going to look at to see how they affect the kind of effectiveness of this algorithm. So there's packet delay and packet loss chance. Those should be fairly self-explanatory. Then there's also the amount of cars and the range of the routers. So that's kind of the range they can connect to each other from. So first, let's just assume perfect communication. Let's say everyone, no packet delay, no packet loss. This is not that realistic, but just to get kind of a baseline. So in these graphs, or this graph, you can see that there's the first value, which is the number of cars, and the second value, which is the connection distance. This is measured in pixels, but you can assume 5 pixels is about 1 meter. So this would be about 16 meters. So as you can see, this orange line plateaus very quickly. By the time about the 1/3 of the simulation is passed, it's pretty much all vehicles know about every road in the network. If we reduce the rotor range to 40, so about 8 meters, it takes almost twice as long, but they do get there, and they do kind of get above 80% fairly quickly still, so I'd still say it's fairly effective. But if we drop the amount of cars in the network, it takes a lot longer for these lines to plateau. And it's interesting as to why. The reason is it has to do with how the cars can get lost on branches of the road network. When there's few cars, one car can get stuck in a faraway branch in the network and kind of not talk to anyone. So the other vehicles might know everything in the network, but this one is just super isolated and they don't get the chance to talk to another one, which causes kind of these issues of it never really plateauing or never really capping out. So let's add packet delay and packet loss. So the first value is the packet delay in ticks. So about 60 ticks is 1 second. So 10 ticks would be a sixth of a second for packet delay. And then 5% packet loss. So if you look at all these graphs, you'll kind of notice that changing the packet loss and packet delay barely matters. In each of these graphs is perfect communication, just no packet delay and no packet loss, and it's right with the rest of the numbers. So why is that? That's kind of weird. Well, the reason has to do with stoplights. When vehicles stop at stoplights, it doesn't really matter what the packet delay and packet loss is. It would only really matter if the packet loss was ridiculously high, above 80%, or the packet delay was 30 plus seconds. But obviously that is almost never going to be the case in the real world. So it ends up being that stoplights are just the perfect time for vehicles to communicate and propagate the knowledge to each other, and just gives them ample time to do so. So it ends up with the effect that packet delay and packet loss do not matter and don't affect the network pretty much at all, which is very nice for us. So what are some real world applications of this technology? So for starters, maps installed on vehicles can become out of date, especially if the manufacturer stops providing updates to their vehicles, which can happen, especially a problem with older vehicles. And there's other services already like Google and Apple Maps that are centralized. So how does this improve over them? So again, this is completely decentralized. So there's no servers, all the costs are on the people using the cars, which, just communication costs, which would be fairly low. And then there's also no need for a constant internet connection. We just kind of need to be near other vehicles, which if you're in a city will be all the time. You're never going to really be far from someone if you're in a city. And something that might be true is that it might propagate road knowledge faster than centralized services. It's hard to measure how quickly they do, but in this system, once one vehicle has traveled down the road, it will start propagating it out to everyone else, which is fairly quick. We just need one vehicle to travel down one road. Obviously, if you want to have some more if you want to have more validity in that statement, you'd need to have more vehicles go down there to confirm it. But it might be possible that this does propagate road knowledge way quicker than a centralized service. So what are some future extensions to this kind of simulation? So one of them would be adding maldoers to the network to kind of see what effect they would have. Is it possible that they could overthrow the network? Could they lie about the road network enough that a bunch of the good Samaritans could be completely fooled? That's something that's interesting to look at. Something else that's interesting is that instead of sharing road network information, propagate traffic knowledge. So Google Maps and Apple Maps already do stuff like this, so this would just make it more competitive with that, with those services. And the third one, kind of extension would be adding car accidents, construction, and other road hazards. So In Winnipeg, we have construction all the time. We have a bunch of terrible drivers, so there's accidents constantly, especially during winter. And there's potholes everywhere, so there's literally road hazards like on every single street here. So this would really just make it more accurate to Winnipeg. But that could be something that's interesting to look at. But we'll just end this with looking at a demo of the kind of simulator in action. If it wants to full screen. No? Okay. And in this example, you can see I click on a car every now and then. That it just essentially allows me to look at what it knows about the network, like what roads it's kind of been told about or what it's seen and driven on. So you can see here I'm looking at that one of the vehicles that's just coming around the corner right here. And you'll see as he runs into the rest of these vehicles, he'll learn about pretty much the rest of the network. You can kind of see that looking at the output, we pretty much all know everything about the network. There's just kind of this one road here that people aren't really that familiar with. But once a couple cars go down here and kind of travel along those roads, everyone will know everything about the network. All right, so that is my project for computer networks. I hope you enjoyed.